Yeah, here we are. Let's see. There's one more thing that's not good. And that's this one. Right. Can you hear me?
Yes.
Yes? Very good.
Yes.
So, I'm back home again. And I'm trying something new. I'm standing. So I took an hour to prepare, and still at the last point things didn't really go as planned. So I hope everything works out. Um, could you repeat something? Just say to me, so I want to make sure that I can hear you correctly in my earpiece.
Test, test.
That's very good test. Good. Okay, so I'm back again in my son's bedroom. Um, it looks like a lot of space, but I can't step back because his bed is here. So we'll just see how well this goes and if I don't fall over. Today, can you hear me properly, by the way?
Yes. Yeah.
Yes, very good. And maybe, okay. So let's see if the switching works. The mute all button is quite a long way for me, so try to be conscious of your microphone to stay quiet, and if you want to ask something you can interrupt me. So for today we have the non-parametric tests scheduled. So what we've been doing up until now is always looking at the parametric tests. So the t-tests that we've been doing, the ANOVA, all assumes a lot of they both have a lot of assumptions on the distribution of the population, of the test statistics. And today we're going to look at a non-parametric alternative. So if you look at the field, the test workflow chart that Field has in the back of the book, there you always see that you get pointed into a specific direction, and that you also have a non-parametric alternative in some cases. So today we'll be covering the list of non-parametric alternatives just to add to your toolbox, to your statistics toolbox. So that we will be covering this for today. And let's see. Yeah, here we go. I have to click this. Where am I? Yeah, I'm here. This still works, right? You can see it moving. Yeah. Go one back. So the non-parametric tests, and what I want to go over is the things that the non-parametric test is, the differences, just to have an overview, and then what I want to do in this part of the lecture is just go over a few of the, how would you say that, the building blocks that non-parametric tests use to do the analysis, and where it makes it possible not to have such strong assumptions on the non-parametric tests. So we have the normality of the distribution is one of the assumptions that holds for parametric tests, but for non-parametric tests this is not really an issue. And I wanted to also go into the things that need to be the same also for the non-parametric tests, and that is of course the fact that your sample as we take it should be a random sample, because only when we apply a random sample we can the null hypothesis testing as we stated it will hold, because and that's something that sounds very obvious, but if you're looking into questions about intelligence and difference in intelligence scores, then this is something that quite easily gets confused, because when you if it really is a random sample and you want to generalize to the total population, then that means that it should be a random sample from that total population. So if you do research and you only focus yourself on the psychology students, for example, your university students, then that would mean that you don't have essentially a random sample because it's it's a restricted sample. So you need to take this into consideration while generalizing, and that holds for both parametric and non-parametric tests. One thing is, if you find yourself in that situation that your research subjects are very specific, then you could at least alternate your hypothesis and your generalization. So instead of generalizing to the total population, you could state in your research report that you're only generalizing to this specific subset of the population. So you're, for example, the psychology students as your subject. So you should take that into consideration. The other thing that differs is the sensitivity to outliers. We've seen, we're gonna see when we're going into the regression analysis, that if you have a extreme outlier in your regression model, then you it skews the entire regression slope. So where for example, if you have no outliers and you have a regression slopes that goes a little bit like this, then if you only have one outlier that is quite extreme, so meaning with outlier that the expected value is way off in terms of what your actual value is, it could skew your entire regression slope. So it could skew the way your model actually fits. And parametric tests are very prone to this. So we try to take those extreme values out, as you will see when we get into the block for regression. But for non-parametric tests, this is not really an issue. So this solves this problem. It also works, and it's a bit of a stretch, because the non-parametric tests works also very good with small samples. We've seen with the t-test, for example, that even for small samples we can have a correction and see the tails inflated, the way the t-distribution is shows its tails when the degrees of freedom are quite low. But in general, if you have at least 30 participants in your cells, then it's mostly okay within the parametric testing. But when it is a bit smaller, then it could become problematic, whereas the non-parametric alternatives, it's not really a problem for these. And the last one, and I find it's a bit of an arbitrary point at this stage, because the parametric tests are set to be faster in the way it's calculated, but and that the non-parametric tests are a bit slower. But we now have such computing power that this is not really an argument anymore that would hold. I'm seeing some questions in the chat, but it's way over there. So if anyone really needs to voice this question, then do it through audio, because I can't read it from here. I have to step out of the frame. So this is for me also a test. If it doesn't really work, I will go back to sitting down next time. Okay, is that clear? Those distinctions?
Yes.
Yeah,
yes.
Very good. Okay. Let's see again. We're here. Oh. So, for example, what we have here is two vectors that I've shown here. Let's see. I can enlarge it. I think vector x and vector y, and this one has actually no outliers, but this one has an outlier. I'm looking if I have maybe skipped one slide. Yeah, this one. So the outlier here is, so the two vectors are essentially the same, x and y. It's 1, 4, 6, 7, 8, 9, and 39. And that the 39 is actually, well, it's a planned outlier in this case. But this 39 will have significant impact in the way the model fits. Of course, if this is a value that was not actually possible within the scale that you're measuring, then you would have to take it out. But assuming that this would be a possibility within the scale, such an outlier would have an enormous impact if the rest is non-problematic in that sense. So if we plot these two vectors in a box plot, then we can see here that we don't have any outliers in our box plot, but in this one we see the 39 being in the extreme values over there. So the thing that the non-parametric tests do essentially is rank the scores that you attained. So it's in essence ordering those scores that you have from low to high. So in R you have a function for this called the rank function, and we see that if I rank the x values and I also rank the y values, then an ordering is applied, and we will see that the ordering values for both x and y are essentially the same. We start with the lowest, then the next one, then the next one, then the next one, and to the end, and that means that we only had in this case 6 values, so there is not so that you see that the outlier is essentially taken out of the equation. Now that would be quite easy, but there are some things to take into consideration, and the thing is that it could be the case that you have ties in your data set, which means that the values, the scores that you have obtained are actually the same exact scores for 2 people or even more people. So what do you do with these ties? And there's a very specific way that R handles this. And the ties are handled as follows. So the first thing that is done, and I will try to show it here, is that if we just have our x value, and I've created a new x value, x vector in that sense, with the values 1, 4, 6, 7, 8, 8. So this is 2 times 8. We have a 4 again, we have a 7 again, and we have a 9. And if we want to apply the ranks as is done in R and apply these corrections for ties, we have to go through the following steps. So the first thing is we have to order these values. So if I order them, then the lowest value that I have is a 1. The next value that I find is a 4. The next one is again a 4. Then we get a 6. We get a 7 and another 7. We have 2 8s, and finally we have a 9. So that is essentially putting them in order. Make sense?
Yeah.
Yes.
Okay. Now the next step is that based on the order that we just created, we are going to make a non-tied ranking. So we are going to assign integers in ascending order, starting at 1, going to the amount of observations that we have. So in this example, we're going to start with the non-tied ranks. We're going to start with 1. We're assigning a 2 to the next one, a 3 to the one after that, then a 4, a 5 for the first 7, a 6 for the next 7, a 7 for the following 8, an 8 after that, and we have the 9. So we've now essentially ranked these numbers, but we've not corrected for those ties. We've not corrected for the fact that some of these values are essentially the same. So the final step, and this is where you actually correct for ties, is the ranked orders. And what we actually do is we look at, for example, these two. These are both 4s. We've assigned a non-tied order of 2 and 3. And what we essentially do is we add these two up together. So we add 2 and 3. and we divide by 2, and 2 because we only have 2 of those ties, which lands us at a 2.5 for both. So essentially it's averaging on the ties what we're doing here, and that's essentially what we're seeing here. We have the 2 plus the 3, and we divide by the number of ties that we actually have, which lands us 2.5. And that also counts for the next one. We had 2 7s, and in the non-ranked order we assigned a 5 and a 6 to these. So again, if we add those two together and divide by the 2 ties that we have here, we end up with 5.5. And finally the same step for the 2 8s that we have. We add those 7 and 8s, divide them by 2, and we get 7.5. So it's shown below that for these ties, we just add them together, and then we have essentially the correction for ties applied. Can you follow that?
Yeah.
Yes.
Okay. I do have a question though, because I understand the last part, but can you go back to the slide? I can't see it anymore.
Yeah.
So the non-tied rank essentially is just like numbering up how many values you have, because there's 9 values. Okay.
Exactly. Yeah.
Okay.
So the non-tied rank is just you start at 1 and you go to the end, and of course the order of the ones that are tied, that are the same, that doesn't matter. So you are essentially getting rid of that notion of order, because you're applying these rules to tie. You're averaging those out and assigning the average of the ties to both. So there's the order essentially disappears. Is that clear?
Yeah, thanks.
Okay.
Sorry, can I ask another question?
Of course.
I probably missed this. I'm sorry, but what's the point of doing this? Making
the point. The point of doing non-parametric tests, or the point of making ties, correcting ties.
Oh, okay. Okay, thanks.
No, it's a question to you. So is it about the non-parametric test, why you would do that, or is your question about why would you apply these ties? Why would you correct for ties?
Oh, yeah, why would you apply ties like this?
Okay, so if you want to work with non-parametric tests, this is the scheme that you have to set up to get rid of the height of the actual numbering that you have, and making sure that the way the non-parametric tests use their notion essentially of null hypothesis testing to be able to apply this. So let's go into an example. So if you have ties, if you have ordering, and you've applied the ranking, and you have applied the ties, you would have and you would have 2 groups. So within this set you would have for example males and females, and never mind what the actual thing is that we're measuring, but if you assume the null to be true, what would your assumption be based on these ranked values? Do you have any idea? Someone else also? So if you would assume the null hypothesis, the null distribution, your critical view on things to be true, then what would you assume for these ranks? If you do divide them into 2 groups, for example.
Probably that the outcome of these ties, or these rankings, would be the same for both groups.
Yeah, absolutely. So if you have 2 values that are actually the same in your final score, you don't want one to be higher than the other. You want them also in your ranking to be essentially the same. So that brings us in essence to the the procedure that you go through with non-parametric tests, and that is, of course, you assume the independent random samples, but then your hypothesis is that your null hypothesis is that you imply that the mean of the ranking is actually equal. So we've created a vector with how we say that. We've created a vector with ranked values, and if you would split those up into two groups, you would assume that the mean of this ranking for the male group and for the female group would be the same, or the sum of the ranking, or anything. At least if the null is true, and there would not be a difference, then you would assume that the order of these rankings would be the same for men and women. So that is essentially the fundamental notion in null hypothesis testing when it comes to non-parametric tests. If you assign ranks, then the ranking order or the mean rank that you would have for both groups are essentially the same. And in that sense, the alternative hypothesis that follows the same line, that it's not the same. It can be different for two-sided tests, or it can be very specific for a one-sided test if you wish. Does that make sense?
Yes, thank you.
Very good. Now, based on the on this ranking, you have to create a test statistic. So we've seen that, and that's the same with the t-test or the f-test that we've seen yesterday. We collect data, but then based on that data, we have to create a test statistics. In the t-value, we use the standard error, and for calculating the f-value as a test statistic, we measure we create the mean sums of squares, and we create the mean sums of squares for the error and for the model to create this f value, which is essentially a signal to noise ratio. That's our test statistic. And within non-parametric tests, we also need to create a test statistics. And what we'll see today is that there are a few test statistics within non-parametric tests, and that they follow either a chi-square distribution or a normal distribution. And we'll go into that when we cover the different types of non-parametric tests. So if you create that test statistic, which is essentially, distributed in like a chi-square distribution, then the same theory holds as we've seen for the f-test, that we could look at what is the distribution of a chi-square distribution if we assume the null to be true. We can create that, and if we can do that, that means that we can compare our found test statistics, and we can calculate what the probability of that specific test statistics is, or more extreme, given that this null distribution is true. So essentially calculating the p-value, and then we check if this p-value is actually smaller than our chosen alpha level that we've applied. So that is essentially the order in which we go through these steps. Does that make sense?
Yes.
Very
Yes.
good. If it doesn't for anyone, you can also state it, right? So it's not just my question for confirmation, but it's also my question to see if my points, if you can follow my points. So if you don't, feel free to mention it to me. Okay. So the next point, going one back, we'll go into a few of these non-parametric tests, and the first one is the Wilcoxon rank sum test, which is essentially the equivalent of the independent sample t-test. So it's for independent two samples. So if you have a violation on your assumptions for the t-test, for example, that your variances are different and that it's not normally distributed, then you could go to the non-parametric alternatives in this case to create, to still run your analysis. And this is the Wilcoxon ranked sum test, and we'll go into this one. And every time, going back one. So what it essentially does is if you measure, well, something, some x, then these values that you actually collected are first ranked, and they're ranked in the same way that we've just described. You order them. If there are ties, you solve for these ties, and with those ranks that you've created, you look at the sum of these ranks per group. So because they are two independent groups, you would add the sums for one group and then add the sums for the other group of the newly created ranked variable. And of course, under the null hypothesis, you would assume that these values would be equal for both groups. In the next step, you standardize this difference, and then you can use the standard normal distribution to essentially test this hypothesis. And for this, I've had always in the lecture hall, I would ask you to come down again, and we'll make this more clear. But again, because we're not in the lecture hall, I will show you the example from last year, and I have to see if this works. Moving over to this one. Let's see. Yep, this is working. The question of, again, if you can hear it if I start playing this. I haven't started it yet.
ANOVAs. When we started with the one-way ANOVA,
yes,
yeah.
We can hear.
We went into to determine if there is a difference in height between men and women. And I want to do that same analysis again, but now for the non-parametric tests. So for that test, I need two rankers. I think you both are very good rankers. So if you would please, yeah, you too, yeah. Both, right? We need two rankers. So please come down, have a round of applause for the rankers. Yeah. But of course, we also need men and women. So I need a couple of men and a couple of women to come down. And we will have this experiment here, and we'll do the calculations. So, men. Yeah, you need to come down. You? Yes, we need more men, right? You three, of course. And we have a man there. It's not very gender neutral, I know. I'm sorry, but it's just for the experiment. You too. You're a man too. So come down. Yeah. Okay. So, do we have enough men? We have one more? Yeah, come down. Very good. So, let's see. We need to rank. So I want to ask the rankers to rank these people based on their height. So make sure you choose a side, of course, and make sure that you rank them in the correct order. So try to put the highest at that side and the smallest on this side. Yeah, just get them to the right place.
But now we put the high ones here.
You put the high ones there, okay. And then maybe you could already start with the smaller people. And yeah, go. Yeah, that way. And highest at that side. Is this going good? Yeah, very good. So we are the ethical committee, and we have to see if this is going well. No, no, so sorry. Yeah, okay. Is this good? You think it's good too? You're okay with this? Yeah, all right, okay. We're not done yet, right? So, I'm going to count. I'm going to give you a number, and you have to remember that number, right? So, you're 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, you got it? Okay. Now for the rankers, you have to determine which people are the same height, so you solve the tie issue. Yeah? Okay, so but with solving it, I mean you're the number 3, 2, and 3.
Yeah.
So
it's
yeah. So now you have to remember your new number, 2.5, right? So and
2.5, and that I was 4, 5. Yeah. So 4.5.
that's it. You agree? Yeah. So you all have your new number. There's still some confusion here. Are you okay? Right? Yeah? Okay. You still have 6. Okay. So, in terms of null hypothesis testing, and assuming that the sum of the ranks would need to be equal, well, we already see that, well, if the null would hold, then the distribution of men and women in height would be spread across, right, across the whole range. So we already see, in terms of null hypothesis testing, that, well, something is going on here. So what we need to do now is get all the men in one group, you as rankers, and get all the women in one group. And then, if you got that, then you have to add up the ranks.
Yeah.
Yeah? So one, get the women on this side and the men on that side. Okay, very good, very good, very good. Yeah? So what is the sum of the ranks for the women? 22. And for the men? 56. Yeah? How many women are there?
6.
How many women are there? 6, right? And how many men are there? 6 as well. Okay, so again, coming back to the null hypothesis testing, if you expect under the null the sum of the ranks to be equal, well, this shows it's not equal, right? So we need to test this. And
okay, we're stopping here. I'm trying to get back to my slides now. Here we go. Yeah. So, did you see the one sneeze? I was like, oh, he's standing next to everybody. You're still there?
Yes.
Yeah, very good.
Yeah.
So this is the essence of this test. You rank these people, you put the groups together, and you add those sums up. And we're going to look at that from another example that I've created based on some simulation. So I'll skip the actual simulated values. But no, let's have a quick look at this. So what are we actually simulating here?
Can I ask something?
Of course.
So why would you have to assign ranks to everyone? Like, can you not just put everyone based on length from 1 to 10 and then divide it between males and females? You don't have to subdivide between the equal length to different ranks. Does that make sense?
It does make sense, but so it's debating if you need to solve for the ties, right?
Yeah, basically. Yeah.
Yeah. So for example, if you would have a man and a woman that have that are equal height, and then you assign an increasing number to them both, and one gets in the male group and the other one gets in the female group, and for example the male was to the right side and would have a higher number, then that would influence your expected value, right?
Yeah. Okay. Fair
So
enough. Yeah.
yeah, okay. So going back to this, what are we simulating in this example? Anyone? In terms of
I don't know.
no, okay.
If
I'll
one group gets ecstasy, the other group gets alcohol.
yeah, that's true. And then what is our dependent variable?
A depression.
Exactly. So in this example, we're trying, and that's the simulation. Very good. We have two groups: a group who gets ecstasy and a group who gets alcohol, and we're measuring their amount of depression. Very good. Let's see. We're back here, and so we have the depression scores on this column, and we have the factors. So to which group you belong, either ecstasy or alcohol. Let's see if I can push this button. Yeah, ecstasy or alcohol. And what I've created here is, let's see, I can go one back. Yeah, I already assigned here at the bottom a new variable called R in terms of rank, where I applied the rank function to the depression scores. Make sense?
Yeah.
So what we're seeing here is that we've also created a column, which is the ranked. So it's the ranked order for the depression scores. And what we see is that if we, so what we see here is that if we order those, we of course see that these depression scores are equal, 26, 26, 26. So the rank that we have is 2. Do you understand why? Is this clear? Why it's 2?
Because you one got the 1, the other one was ranked with 2, the other with 3, and therefore the mean the mean
Very
is
good.
2.
That's it, exactly. And that holds for all cases where the actual values are the same. So we have a depression score of 27 again and again and again and again, and we add all those up and divide them by the numbers of people that actually have a depression score of 27, and this will get us a rank score of 6. So that way we see that there are a lot of ties in this example, and that's on purpose to show you this, of course. But what we see here is that we created the ranked based on the solving for ties, as we explained earlier. Now, the rest of the calculations will focus only on this ranked, this newly created ranked variable. So what we're doing is first calculate the sum of those ranks, because our assumption was that if we've created two groups, height for men and women, or in this case the ecstasy group and the alcohol group, then if the null hypothesis would be true, then we would expect no difference between these two. So adding all these ranked numbers together for both groups under the assumption of the null hypothesis should yield kind of the same results, right? So that's what we're doing. I'm using the aggregate function here, and what we're getting is for the ranked numbers for alkyl and ecstasy, one is 102 and the other one is 108. So these are pretty close. So I'm betting that if I do essentially some testing, significance testing afterwards, that these will probably not be significant because they're very close. You agree with me?
Yes.
Yes, but how do we know when something is too much of a difference, and when they are close enough?
Yeah, so that's the thing that we want to discover. So we can actually apply statistical testing based on these values. So we'll go into this exact point by the following in the following slides, and let's see. I'm going to the next one. Oh, that's too much. It's skipping a few I've skipped a lot. Sorry. So what we actually want to calculate is the test statistic based on those two values. And the test statistic here is called W. Any idea why it's called W?
Because that's the name of the test.
Yeah, that's Will Coxon, right? So that's the goal of the ultimate goal of every statistician, to get their letter as a test statistic. Well, okay, so we have to determine that what W actually is. So if you look at this, do you have any idea what we actually want here? What is actually needed? What is this formula saying? Anyone?
It sums up the lowest ranks for. Oh no, it minimizes the sum of the ranks for both groups.
Okay, so what are you saying in this? So you're saying the sum of the ranks for both groups. So I totally agree with you. So we have group 1, and we want the sum of those ranks, and R is the ranks, and this sub is for 1. So R sub 1. So that's the sum of the ranks for the first group, and we've created that already in the previous slide. So we now have the sum of the ranks for one group, and we have the sum of the ranks for the other group. So what does this minus do then?
It gives lowest rank, so one group or the other.
Exactly. So you have two numbers in here, and what the minus function essentially does is returns you the lowest value of those two. That's it. So it's no rocket science. And if you look at R and what it's doing with using the minus function is, and this is a vector of those both those two values, it just returns the smallest. So the lowest value of those two is of course 102. We've seen that of course in our example. So we've seen that one was 102 and the other was 101. But if you want to actually calculate it with R, you could use the minus function. And that is essentially the test statistics that we use. Make sense?
Add something?
Yeah, go ahead.
I still don't understand what you mean with minimize. So what does 102 exactly show?
No, it's not minimizing, it's just selecting the smallest. So
Okay,
you
so
have
this-
so you have two numbers. The one was 102 and the other was I think 108. So which one of the two is the smallest? Well, 102. So this minus function just gives you the smallest of the two.
Oh, okay. Okay,
It's quite
thank
easy.
you.
Yeah, very good.
So when would you actually use this? Because obviously when you have two groups with two values like this, it's very easy to see it by yourself. But when would this come in handy?
Well, for this specific example, it's with this Will-Coxon test, it's always only two ranked sums, right? So, but you could imagine, and you'll see in a minute, that sometimes you have more than two that's with different non-parametric tests. So it's handy to quickly find the lowest value. But also programmatically, it's easy to use the function for creating for getting that out instead of just having to do that manually. So it's in that sense computational convenience in that sense. Okay, we're not done yet because we have to essentially we have to standardize this this score that we've created, because it's the W value is essentially an unstandardized value, and we have to go from the unstandardized to a standardized value, where the standardized value actually means transforming this value into a z-score. And so to calculate the z-score, we need to standardize this W value, and to do so we need the mean, of course, of this W, and we also need the standard error of this W. Just like you would standardize every value, you need the mean and you need the standard deviation of those. So for both, we need the sample size for each group, and that we have to calculate. So we're applying the length function here to get the sample sizes for both group 1 and group 2. So the group that gets alcohol and the group that gets ecstasy. And that is the standardization step that we need to do here. Let's see.
Do the two groups always have the same number of participants?
No, it doesn't have to. It can be different.
Okay.
In this case, it's the same, but it can be different. So calculating the mean value here is the mean with a bar on top of the W, and this is actually just because you're ranking the height of the values actually doesn't matter in assigning a rank. So we can get to the mean of this this W value by only using the sample size of both groups. And well, we will not go into the details why the calculating the mean for this one is defined by this formula, but the thing that you only need to know is that this division by 2 and the addition of 1, they are constants, so they don't change based on your sample size. The only thing that changes here is the sample size. Could change in different samples is of course the sample size itself. So if you apply this, we can get to the mean of W by just applying this in R, which will get us the mean value for W, which is 105. And then in the next step, we'll have to calculate the standard deviation, or the standard error, sorry, of this W. And the way this is calculated is both, again, using only the sample sizes for the different groups. So we apply this, we square it in R, which will yield us the standard error for this part. And with these pieces of information, we actually have enough to calculate a z-score. And that is what we'll do.
About the mean.
Mm-hmm.
So I find it a bit confusing because you said that the W is the lowest score. So how can you actually get a mean from that if it's just one score of the 102?
Mm-hmm.
Then
yeah, so
what does the mean? What is the mean and what is the standard error then?
Yeah, so the mean essentially, assuming those groups to be so your hypothesis would be that those averages on those groups would be essentially the same. So we're now actually calculating those for one group. So look, and that's the thing, because you're and yeah, I understand your confusion. It's because that we use this function to just select the lowest, but we might as well have the highest as an example, because they should be interchangeable if the null hypothesis holds. And it probably in this case it does, but it could differ. But the way this is set within this non-parametric tests, it's based on the smallest value. So you should, I think, if you do it for the highest value, then you should have a slight variation on calculating the means for the highest values. Yeah, so don't worry about it too much. It's just, for me, it's more important that you conceptually understand the notion of where we have to use a mean and a standard deviation to transform this value into a z-score. And if you have that, then you have enough information to actually test it.
But is
thanks.
like the W mean then sort of like a theoretical value and the
No.
standard deviations?
No, it's based on the sample size. But if you just order, because when we are thinking about mean, we're always thinking about calculating a mean in the parametric paradigm, where we're thinking about higher numbers having actually a higher meaning, in the sense that 4 is double the distance to 2, for example. But if we're only ranking, then the step size in between is always the same. So you can calculate a mean without the need for looking at those different. You can just do it with the sample size values, essentially.
Okay.
Yeah.
Oh yeah. Okay. Thank you.
I also have a question.
Go ahead.
A very quick one. In the standard error formula, there is a 12.
Yeah.
And the 12, is that the sample size?
No, it's a constant. So you will see with a lot of these.
You can't see the slides at the moment.
No, I know. This. Here we go. You will see with the non-parametric tests that there are quite a few constants in this formula, so they don't change. So everywhere where you see an actual value like 12 or 1, these are constants within these calculations. Okay.
Okay.
Yeah.
Thanks.
Yeah.
And so I should read this as the square root of the first sample size times multiplied by the second sample size, and then multiplied by whatever is the sum of that plus 1.
Yeah, exactly.
Okay, because you said something about squaring it, but that was
the square root, I mean. Yeah.
Okay.
Sorry.
Okay. Yeah.
My bad.
Yeah.
Okay. So we're almost there, and in the next step, I think you will see why you would need the mean and why you would need the standard error, because we're essentially applying the same trick as we do with all standardization steps. Is we're calculating we're calculating the z-score by having some value, subtracting the mean of that value, and dividing it by the standard error of that vector. And here we are essentially doing the same. So it looks exactly the same like when we did with the t-test. And if you would do that with the regression analysis, it's also the same for calculating a beta coefficient, for example. So it's the same trick that we are applying. So we have our actual W score, we have the mean of the W, we have the standard error of the W. If we apply this, we get a Z score, and that is what we're doing right here, applying the Z score. And the Z value is standard normally distributed, right? So that means that we can apply again the basic visualize function and the Z. So it's a standard normal distribution. So we apply the visualize norm from normal, and we give it the Z value, and we can set the section to lower or to tails if we would like to test two-sided. And that will yield us our p-value. And we've already seen that the difference that we had was quite small. And that is what we're seeing here again. So if we look at this is the p-value for a Z value smaller or equal to -0.22. which is equal to a p-value of 0.41. So it's a little bit less than half of the observations under the null distribution. So this is most definitely not significant. We could also test two-sided, of course, using the same visualize function. Then we have to give the visualize function a positive and a negative z value, and we set the sections to tails. I saw a question, I think in the forum, or someone mailed me if it matters if this a negative number goes first and the non-negative goes second. I think it doesn't matter, so you can interchange these both, and you will get the same results. So if we do that, then we end up with this. And I showed this graph to my son once. He's now 8, and I think it was last year that I showed it to him, and he said, "Well, it's a tent." And it looks like a tent, yeah. I thought it. Yeah. So two-sided test, of course, both not significant for these. Because we're just dealing with a standard effects, with a standard z-score, we can also calculate the effect size for that standard z-score, which is done by dividing the z-score by the square root of the total sample size of n. So if we do that, we can find our R effect size value, which is, of course, again, totally nothing, because there actually isn't anything going on in this sample. So those are the steps for this Wilcoxon test. What I wanted to mention is that this Wilcoxon test actually does the same thing as the Mann-Whitney's the Mann-Whitney test, and SPSS uses this Mann-Whitney test, which does essentially the same thing, where you calculate this test statistic, but then you get a test statistic called U. Go back. Then you calculate the mean for the test statistic and the standard deviation for the test statistics, and essentially you use that again for transforming this into a z value. Come on, go down to the next slide. No, it's not working. No. Let's see. We'll do it with this way. No. It doesn't want to go to the next slide. Absolutely. Okay. So essentially you transform this to a z-score, and then again it will give you the results just in the same way that it does with the Wilcoxon test. So that's the first one. We have a few more, and we'll cover that in the next part. But first, we are absolutely needing coffee. Don't you agree?
Agree.
Yes.
Okay.
Yes.
We'll be continuing 10 minutes past, right? Okay. See you in a bit.
Can I ask a quick question, Real?
Very fast.
For the mean of W,
sorry?
How do we know, for the mean of W, for
Yeah.
calculating that, how do we know which group to use as N1?
Let's see. We're getting here. Going back up again. For the mean of W. So it's this one, right?
Yeah.
Yeah. Yeah, that's a good question. It's the n associated with the smallest group.
Okay, perfect. Thank
Yeah?
you. Yeah.
Okay, you're welcome. Go get yourself a coffee.